Chapter 13, The Logic of One-Way Analysis of Variance. Here is our illustrative example. Researchers studied whether pets can moderate stress responses. Participants were monitored after a psychological stressor. Group 1 was in the presence of a pet dog with a mean heart rate of 73.5 beats per minute. Group 2 had a human friend present, averaging 91.3. And Group 3 was alone, averaging 82.5. These means look different, but how do we test whether the differences are real? With 3 groups, there are 3 possible pairwise t-tests. We could test group 1 versus 2, 1 versus 3, and 2 versus 3. But here's the problem. If all 3 null hypotheses are actually true, and we test each at alpha equals 0.05, the probability of retaining all 3 is 0.857. That means there's a 14.3% chance of at least one false rejection. That's almost 3 times the intended error rate. This is the problem of multiple comparisons, and it's why we need ANOVA. The more groups you compare, the worse it gets. With 2 groups in one pair, the family-wise error rate stays at 0.05. But with 3 groups and 3 pairs, it jumps to 14%. With 5 groups and 10 pairs, it's 40%. And with 10 groups and 45 possible pairs, there's a 90% chance of at least one false positive. This is why ANOVA is essential. ANOVA works by comparing 2 types of variation. Here are the 3 group means plotted on a number line, with the grand mean shown as a dashed line. Between group variation measures how far the group means are from the grand mean. This is the signal we want to detect. Within group variation measures the spread of individual data points around their own group mean. This is the noise. If the signal is large relative to the noise, ANOVA will declare a significant difference. The ANOVA hypotheses are straightforward. The null hypothesis states that all K population means are equal. The alternative says at least one mean differs from the rest. Importantly, the alternative does not tell us which means differ. For that, we'll need post hoc comparisons, which we'll cover later. To recap, multiple t-tests inflate the family-wise error rate. ANOVA solves this by testing all group means at once. It compares the between-group signal to the within-group noise, and the alternative hypothesis simply says at least one mean differs.